People create a neural network, they train it, and then they evaluate it. But the question that I have is, how smart a newborn neural network is before even training it? So today we're going to answer this question, how smart a newborn neural network is. Stay with me. Right, so in the previous videos we have coded a MRI Pytorch dataset class. We have coded a convolutional neural network in Pytorch. And in this video we're gonna actually create an object of our convolutional neural network class and also create an object of our dataset class. We're gonna normalize the data inside our dataset class. We're going to put our model onto our GPU, so very exciting stuff. And then we will define a Dataloader to actually iterate through our dataset object and pass the data into our model for testing it. Remember, we are not going to train this model. It's going to be absolutely dumb, beautifully dumb, right? So let's just get started. I'm going to first of all create a dataset object, right? So it's going to be MRI dataset using the dataset class that I've defined before. So if you remember, the dataset class was named MRI. I mean, just for the sake of it, let me just show you the dataset object that we've created. So this is our dataset class, right? It has the constructor, it reads the data, it separates tumor and healthy images, it creates an array of ones for the tumor ground truth and array of zeros for the ground truth of the healthy images. And then it would concatenates all the images, tumor and healthy together, puts them into the image instance variable and put all of the labels, all the ones and all of the zeros together and puts them in labels. So there is a correspondence between the two, right? And then we defined this getItem dunder function that, given an index of an image, it retrieves the image, the actual image, and the corresponding ground truth to it, puts them into this dictionary and returns this dictionary as a sample. And then we also define this normalize function that would normalize everything, right? So just as a reminder of the dataset class that we've talked about, and this is also our convolutional neural network that you remember we had CNN layers, we had average pooling, hyperbolic tangent, we've defined linear layers, fully connected layers, and blah, blah, blah. And at the very end, we have a Sigmoid function whose output could be between 0 and 1. Okay, now that we've reminded ourselves of what those classes look like, so here we are defining an object of the class, and then we're going to actually call the normalize functionality inside that object. So this just puts everything between 0 and 1. Let me just see whether it runs. Okay, good. So it runs. Perfect. Next, we're going to define a device. Now, in the previous video, we talked about CUDA tensors, CPU tensors. So we said that we have this ability to put stuff on either CPU or GPU. And by stuff, I mean the data, our model, and so on and so forth, right? So now we're going to define this device. Do we have GPU or not? If we have, it's going to be a CUDA device. Otherwise, it's going to be a CPU device, right? So very simple. So the way to do that, Pytorch gives you this command, torch.device. And then you can set it. So because I do have a GPU, I'm going to put the keyword CUDA. Now, if you have more than one GPUs, you can actually put indices of those individual GPUs, right? But because I have only one GPU, the index would be 0, right? Which means the first GPU, and in my case, the first and the only GPU that I have. Next, I'm going to basically, first of all, create an object of my neural network. So you can actually do it like that. So model equals CNN. And then I'm going to put this model onto my GPU device, or the device variable. One way that you could do that is basically just call the to method. That's right. A model, a CNN model, or a nn.module neural network in Pytorch has this command called to that allows you to simply, just like a basketball, just throw it on whatever device you want to put it on, okay? So here you just literally put your device, and then that's it. you've created your model and it's on your GPU now. If I run it, okay, good, so it's working. Now, next one, we're going to define a data loader. So what was the data loader again? It is just an object that allows you to iterate through your dataset object and shuffle the data, cut it up into mini batches, and so on and so forth. And then you can just grab different parts of your dataset and then feed it to whatever the hell you want to feed it to, right? So the way to define it, data loader. Okay. By the way, I clicked on tab to auto complete the command. Just in case you were wondering. So first we're gonna pass the dataset object that we have created, and next we're gonna define a batch size. You don't have to, okay? In our case, I'm gonna just define a batch size, I mean, just out of habit, really. And in this case, it doesn't really matter because the dataset is really slow, and I'm not gonna train the model, remember. I'm just gonna feed in the data and see what the outputs are. And I'm not gonna shuffle, okay? There's no need to shuffle. So I'm just going to put shuffle as false. And I think by default, shuffle is false. I'm not sure. But that doesn't matter at this stage. Now, next thing. So we run this. Next. Remember, in the previous video, we talked about model.eval and model.train as opposed to one another. Now, we said that model.eval is used when you want to test a model. And we said that it turns off dropout and it makes sure that your batch norm layers are going to behave in test mode. Okay, we explained all of that in the previous video, but we don't have any, batch norm layer or dropout operation, so it doesn't really matter. But it's just good practice to always do this. So model.eval puts the model in test mode, right? And if you run it, you can actually, it also passes, like prints out the model as well. We don't really need it, but whatever. Now, I'm going to create, remember, I'm going to pass in all of the data in my data loader into the model. I'm going to record all of the raw outputs out of this model, okay? So, because of that, I need a list to keep track of the raw outputs of the model. I'm just gonna also define a list that would save the corresponding ground truth values, zeros and ones. Remember, we created zeros and ones in our dataset class. Now, we're going to iterate through our data loader. We've seen this before. How do we do it? It's a loop for D in my data loader. Then, what happens at every iteration? Remember, this data loader is going to iterate through a dataset class. And we said that in our dataset class, we have a dunder function underscore get item underscore, right? And we said that every time we iterate and retrieve a given image or a given sample from a dataset class, that get item dunder function is called automatically. And that's why they call them, I think they call them magic functions or magical functions, something like that, right? So because of that, every time D becomes whatever get item in this dataset object is ordered to return, right? So just as a reminder, again, into our get item, it passes a dictionary. The image of interest living in this index and its corresponding label living in that index as a dictionary, right? So because of that, at every iteration, D becomes that dictionary. So we can actually access the image using the key image in that dictionary and put it into our image, a variable, whatever variable you want. It just grabs the image part of the dictionary. And the other one is, if you remember, as I showed you up there, the key for the labels, we've called it label. And we're going to put that into a new variable. Let's just call it label. You can label it anything you want, obviously. Here's the other very important thing. Remember, our model is living on our device, which is what? a GPU. If I do something like this, remember the dataset does not live on a GPU. By default, everything lives on CPU unless you order them to get the hell out to the GPU, right? So because of that, every time you grab any element of this dataset, you have to make sure that you put them on the same device. In the previous video, we saw what happens if you try to do any sort of operation between two tensors that live on different hardware. Let's say one lives on CPU and one on GPU. We showed that it just doesn't work. They can't just do anything to one another, okay? So they need to be on the same device, living on the same device, right? So we're gonna put both of them on the device variable, which in our case is a GPU. Next, this is the beauty of it. Maybe this is the first time you're seeing this, but so this is our model, right? We've created an object of this class. And you remember that we have defined a forward function that passes the data throughout all of the convolutional and tanh and average pooling layers, and then flattens it, and then passes the result into all of the fully connected layers and whatever it is between, which is your tanh functionalities. And then puts the result into a sigmoid, crushes between 0 and 1, whatever x is, and puts the result back into x and returns that value, right? So, in order to call the forward pass functionality, all you have to do is literally pass your data into your model object. It calls the forward method automatically. Again, another beauty of object-oriented programming. So, all you have to do is, I want to pass all of my data through my model, and that's it. And remember, this image, we have 32 images here and 32 ground truths. Okay, don't forget, this batch size dictates that. So this takes care of the forward pass. Yes, and let's put that into y hat, which is a traditional notation for the outputs of neural networks. And let's also, well, we could actually jump into this. Now, this y hat is now living on GPU. In the previous video, we mentioned how you can actually grab a variable, a tensor, a CUDA tensor, from the GPU, from your GPU, and convert it into a numpy array. We talked about actually this notoriously long command. We mentioned the details and everything. So make a copy on the CPU, detach it from the computational graph, and convert it into a numpy array, right? And we're gonna put all of that, let's append it into our output list. Yes? And the same story about the label. The label is also living on the GPU, right? So what you can do is, again, the same story. I mean, you might as well never put it on the device. I just did it out of habit, to be honest with you. So the label here, we put it on. We do the same with the label, right? And then we're gonna append that into our y truth, which keeps track of your ground truth. One more thing. In the previous video, I said that, look, model.eval does not stop computing the gradients, okay, by the computation graph. But I never mentioned how you can actually do it. Now, the command that you could use is called torch.nograd. Yeah, and the way that Pytorch asks you to implement this is simply by the with command. With torch.no_grad. Whatever you put inside your with command, indent it. It means for this period of time. Pay attention. For this period of time, as long as we are in this sort of part of the code, the computation of gradients will cease, will stop. But the second you get out of with, get here, again, your computational graph is gonna compute the gradients for all of these tensors and operations. So temporarily, during testing the model, it is customary to say, you know what, don't compute any gradients. I don't need the computational overhead. I don't need the memory overhead. I just wanna pass my data through my neural network and just get the output of that. That's all, okay? So, now let me just see whether this runs successfully. Let me just get started from here, just to be on the safe side. Does it run? Okay, ignore this for now. It doesn't matter. We can actually replace this later on. It doesn't matter really. Remember, these are lists, right? But these are lists of numpy arrays. Remember, so this guy over here is a numpy array with 32 elements. Remember the batch size, right? So 32 outputs. Every mini batch will produce a 32 element output. These outputs and the white truth lists, they are lists of numpy arrays, right? So there are different ways that you could actually, get rid of the list of numpy array-ness. So one very interesting command that you could use is called numpy concatenate. Meaning that you grab your outputs list and you concatenate all the numpy arrays within across the first axis, okay? And this literally produces a numpy array that is the result of a concatenation of all of the individual numpy arrays. Remember, each numpy array has 32 elements because you have 32 outputs, right? Now, if I print out the shape of this guy, you see, it is 245 elements by 1. So there's that one extra dimension of numpy that you don't need it, right? So if I print out the first 5 elements of this, you notice that we have 5 by 1 values. You don't need that, right? You don't need this extra annoying dimension. So all you need to do in order to get rid of that is the squeeze command. It gets rid of that extra dimension. So if I were to run this again, and let me again output the first 5, you'll get different values because we're shuffling. You see, that extra dimension is left. And if I were to just look at the shape of this guy, there we go, 245 elements, that's it. No questions asked. So we're gonna do the same for the ground truth. Now, remember, as I said, these outputs are the outputs of a sigmoid, right? So if I were to look at, say, the 21st elements of this guy, it just values between 0s and 1s. But if I were to look at the same thing for the ground truth, it just happened to be 1 at the, in this particular case. But my point is, the white truth, they are all either 0s or 1s, nothing in between. But your outputs, no, they're continuous values between 0 and 1 because they're the outputs of sigmoid. So it is, as you know, in artificial neural networks, one of the things that you do on the output of a sigmoid function, you threshold it. So anything higher than 0.5 will be mapped to the value 1, and anything below 0.5 will be mapped to the value 0, right? So I've defined this threshold function. Have you noticed my pronunciation has really turned into an Irish pronunciation? I said, but it grabs your scores, puts them into a numpy array x, and then any element that is higher than the threshold, in this case the threshold is 0.5, it would assign the maximum value, which is 1, to it. And any element that is below that threshold, below 0.5, it would assign the minimum value to it. The minimum value is 0, right? So let me just run this, and if I were to if I were to run the threshold onto my outputs, right? So this returns the numpy array, right? If I were to run it and just take a look at the first 10 elements, they just turned into 0. I mean, 0s and 1s basically. Now, let me show you. there is this command through the scikit-learn package. I think I have imported this before. Yes, so from scikit-learn.metrics, we have imported confusion matrix and accuracy score, right? These are the commands that will allow us to evaluate the performance of our neural network. So we're going to use those. We're going to use both of them. First one is going to be accuracy score, right? So accuracy score. It takes the ground truth and then the corresponding raw output, or the thresholded output in this case, of your neural network. And then it compares the two. It wants to see everywhere the ground truth is 1, it would like to see the prediction, the thresholded prediction, to be 1 as well. And everywhere there's a 0, it would like to see the thresholded of 0 on the output, right? I mean, that's what we would like to see, right? So that we could say that, okay, the output of our model actually matches the ground truth. So all the tumor images have been predicted as tumor images, and all of the healthy images have been predicted as healthy images. That's every machine learning expert's dream, as rarely as that might happen. Now, the first element is your ground truth, right? And the second element is the actual thresholded outputs of your model. So that is why I'm going to put the command threshold here and pass outputs to it. This guy would return the thresholded values. Now, this will return the accuracy of the model. Okay, so the accuracy is true positive plus true negative divided by everything, right? So everything that's been, predicted correctly on the denominator, and everything else, all the other predictions on the denominator, right? So that's the formula, and this is how you can actually compute this, right? Now, if I did that, what the hell? 35% is just rubbish. It's worse than random. Right? If it was 0.5, we could say, okay, it's like random, right? It's just randomly grabs an image and says, okay, you're normal, meaning that healthy, or okay, you have tumor, right? Just if you did it randomly on a balanced data set, you should get like 50% right? But this guy is doing worse than random, like 37%, and that's terrible. Okay, so I hope that this has been informative for you. If you have any questions, leave them in the comment section down below. If you have any suggestions, again, do the same. Like, share, and subscribe if you enjoyed the video. I see you on the next one. Bye.